So what we're going to be doing is we're going to be just continuing on with this idea of non-parametric methods. These are the methods that we use when we don't think that we can appeal to the central limit theorem. And the circumstances when that would apply is when we have small samples where we have a really good idea that the sample doesn't come from a normal population. And we really have to know that from other information outside of our sample. So these methods are generally pretty peculiar to the natural sciences, where we can have quite a great deal of difficulty collecting large samples. In my own field of research, I generally can get relatively large samples, so I don't have to worry about this. Some of the students I work with in the field, okay, it's a different story, and so for them they need to know about these methods. I've just put an observation down here about something that some people might say, well, when you have a small data sample, you don't need non-parametric methods. You can solve all these problems via a bootstrap simulation. I'm a big fan of bootstrap simulations, and in particular, a particular flavor of doing these simulations, but I don't feel that they give us a good deal of information when we have small samples. In fact, when we have a small sample, we have not very good information about the overall shape of the population distribution. So the bootstrap gives us a very rough measure of that, because it can only simulate from the data that you have. So it's my perspective, and hence I put this perspective on you as the curator of your learning, that while bootstrap methods are useful, they're not a panacea to the problems that we face in the natural sciences. And the classic approaches that we use of non-parametric methods are still valid. So what are our non-parametric methods? Our non-parametric methods are methods that are valid over a much wider range of circumstances than our parametric methods. Remember, parametric methods are our t-test and our ANOVA, and subsequently our regression. Very, very wide class of circumstances that those methods work, and those methods, when the assumptions are valid, are more powerful in detecting differences, if there are true differences, than non-parametric methods. But our non-parametric methods are valid over a wider range of circumstances. As a practical decision rule for using these methods, the thing that we need to recognize is that we largely can just follow a p-value decision rule. So we can specify the alpha level for our tests as 0.05, and if we have a p-value for our non-parametric test that is below 0.05, we're going to reject the null of no differences. We also have to be a little bit careful about the way that we specify the null and the alternate for these kinds of tests. Now, what I've said here is that we really need to decide whether or not we can use parametric methods or non-parametric methods based on intuition and judgment rather than formal tests. And I guess I'm just going to highlight an example here for you. So what I've done here is I've drawn a sample from what I know is a uniform distribution. And I actually haven't made the sample too small. I've made the sample about 30. And so we know that this is not normal, okay? I actually generated the data from a uniform distribution. So I'm 100% certain of what the shape of the distribution is. It is not normal. It's uniform. This is very much not a bell shape. It's a flat curve. So let me just show you what I did. So if I go here, you'll see that I've run this runif is random numbers from a uniform distribution, 30 of them between 0 and 1. Okay, so I've generated it, and so I can reproduce the results. I've set my random number generator to a start. And then I've conducted a normality test on this data, and you can see that the p-value is above 0.05. So if I took my data, which I know is from a uniform distribution, and I run one of my normality tests, the Shapiro-Wilk test is actually, I think I've picked the most powerful test I could find for this. It still doesn't detect that this is not from a normal distribution, that it's from a uniform distribution. So we have very low power when we have small samples. And remember, I've done this for a sample of 30, and by the time we get to 30, we can start to appeal to the central limit theorem anyway. And when we have smaller samples, 10, 20, the problem of a lack of power to detect a difference from normality is much more pronounced. So really, we're going to have to rely on not formal tests, but what we know from the literature. We're going to have to read up. We're going to have to make some judgment. So we're starting to learn that you can't just apply a test and, just go on that. Tests don't work for all occasions. Here we've got a clear example where a simple test of normality is not able to detect that the sample is drawn from a uniform distribution. And most of the samples we have won't be as clear cut as this. They might be a little bit close to a normal distribution. It's unlikely that they would be as quite different as I've got them set up here. So if we move forward, what were the tools? So when we have this idea where we've got small samples from non-normal populations, what do? We have two different kinds of tests that we've been introduced to: the Wilcoxon test for single samples and paired data, and the Mann-Whitney test for two samples. The only real difference from a practical point of view for us is the way that we formulate the null. So we don't say differences in the mean. We use this much more general language of some sort of general difference, okay? Group A is different to Group B. Something like Group A is not different to Group B. So when we use ranks, we can't say anything about the means. Similar situation for our paired t-tests. The length is the same, like the before and after are the same. So really you can think about it as your parametric tests, but just remove the word mean. The other thing to note is that because we're using the ranks of the data, we don't have to worry about anything like a variance ratio tests. Ranks are equidistant from each rank, so that's not a problem for us. So our conceptual approach, what are we looking at here? What do we do? Well, we're going to rank the data from highest to lowest, and really whichever kind of test we implement, it looks for clusters of the ranks. So if all the clusters are ranked at one group are ranked at one end of the rank list and the others at the other end of the rank list, that is evidence of a difference in the two groups. In terms of our testing approach, what do? We formalize a null and an alternate. So male tuner length is the same as female tuner length. The alternate, they're not the same. We set alpha the same way that we have done for all of our other tests and calculate the test statistic. In practice, we're going to use R to look at p-values. P-value of less than 0.05, we're going to reject the null, that the two samples are the same. P-value greater than 0.05, insufficient evidence to reject the null. So in the tuner example, we saw that when we just looked at this data, we do see evidence of clustering. So the males 1, 2, 3, 4, 5. So the first 5 in the rank order are all males, and the last 3 in the rank order are females. So that kind of clustering is giving us evidence that there's likely to be a difference. In terms of all practical matters, we implement the test via the Wilcox function here. So it's just with the data set, apply the test wilcox.test. This is the response variable length. This is my factor on my two grouping variables here. Wilcoxon rank sum test is telling us what kind of test. And we look at the p-value. The p-value is less than 0.05. Therefore, we reject the null that the two samples are the same. Okay, so this is what we focus on. And it's just, very, very simple or very, very similar to the t-test. The other example I showed you was with coral reefs. So we said this is a before and after test. We took some measurements at sites before and after. Small sample. We're worried that it's not from a normal distribution. We're worried about that from some other research. What do? We want to create a plot. Because we have a paired test, we're going to use a horizontal box plot, formalize a null and an alternate. Cover before is the same as after. So nothing about means, just the same before and after. The alternate, not the same before and after. And of course, we can look at the data to decide which one is larger when we actually look at the data. And we implement the test in R. So what does our plot look like? Our plot we used is of the data, not of the ranks. Okay, so we're just going to do exactly the same kind of plot that we have used for our parametric test. So that's really quite easy for us. We look at the data, we get the ranks when we have a negative difference, the ranks when we have a positive difference. We sum those values up. You can see here that there are many more positive than negative numbers. That's a sign that we're going to have a significant difference. How do we implement the test? Very straightforward. So you can see with my data set, apply the Wilcox dot test. My measurements were labeled, you can see up here, column before and a column after, and I set the paired function to true. You can see that there were some ties in the data set, so it gives us these warnings. We don't really have to worry about those warnings too much. We just look at the p-value decision rule and we say that for this sample, there is sufficient evidence to reject the null. And we actually know that from our plot or our analysis of the data, we calculated the means. So even though we're doing a non-parametric test, we might still calculate the means or the medians for our samples. We can actually work out that after the period after the heat wave event that we're looking at, there's been a deterioration in coral cover. And that is an opportune time for a pause.